In this video, we're going to do the free response at the end of page 13, 2004, number 5. And so in this problem, it says the graph of the function f shown above consists of semicircle and 3 line segments. So just make a mental note, this is f, not f prime, but just f. Let g be the function given by, so g of x is this integral equation, where if you notice they're integrating f, which is what you have here. So the first problem, part A, says find g of 0 and g prime of 0. So for g of 0, that means you're just using g of x and you're plugging 0 in for x, not for t, but for x as the boundary. So g of 0 is going to equal the integral from -3 to 0, plug it in, of f of t dt. So how are we going to find this integral? If you notice, f is this function, so how do you find an integral from a graph? Well, an integral is the area. So when we integrate f, that's going to equal the area from -3 to 0. So -3 is right here, to 0 is right here, so we're finding this area under our graph to the x-axis. You notice that's a trapezoid. So we have a formula for area of a trapezoid. You need to have this memorized. 1/2 times the height times base 1 plus base 2. So if we label this, our base would be, our height is this distance, because our base is the 2 parallel sides. So since these are the 2 parallel sides, that is not parallel. These are the bases. So it goes up to 1 and the other base goes up to 2. Our height would be this distance, which has a length of 3. And we would plug that in. So this g of 0 is going to equal 1/2 times the height, which is 3, times the bases added together, 2 plus 1. And if you evaluate that, it'd be 1/2 times 3, so 9/2. Okay, so then it asks for g prime of 0, which first we need to determine what is g prime, right? So how do we know what g prime of x is? Well, given g of x. So we're taking the derivative of an integral. So this is that second fundamental theorem of calculus. So g prime is going to equal the derivative of this integral function. Oops, one side I did a bracket, one a parenthesis. So when you take the derivative of an integral, we know that those things are each other's inverses and cross each other out, but what is that second fundamental theorem? That you take this top boundary, if it's a variable, if it's in terms of x, and you plug it in, you replace whatever the variable is on the inside with it. And then technically it's chain rule, right? So what we said on the notes was when you do the derivative of the integral from some boundary to g of x, let's say f of t, well then that's going to equal, you keep the same function, since those canceled, you don't do the derivative or the integral, but you replace the inside with your top boundary, and then you do times the derivative of that top boundary, whatever you plugged in. That's the second fundamental theorem. The function itself stays the same. So over here, these cross off, we're keeping this just f, but now we're replacing t with x, and then times the derivative of what we plugged in. But the derivative of x is just a 1, so it's just f of x. So what does that mean? Is g prime of x just equals f of x. So this is f of x, which now we know is also g prime. So it's like they give you the g prime graph, if you're talking about g. So we want g prime of 0. So g prime of 0 just equals f of 0. Well, we can just go to our graph and get that point, right? Because this is f. What is f of 0? Here's 0, so f of 0 is 1. And that would be that answer. Okay, so for part B, find all values of x in the interval at which g attains a relative maximum. So how do you know where you have a relative maximum? Because think about it, we're talking about g now, so we don't really want to think in terms of f, but how do we find a maximum of g given g prime, given the derivative graph? So now we're looking at a derivative graph. A relative maximum is when g prime goes from what? Think about a maximum. The slope changes from positive to negative, which the slope is the derivative. So when g prime goes from positive to negative. So it should be an x-intercept, but specifically an x-intercept that where it goes from the positive above the x-axis to below the x-axis. So where does that occur? You should be looking at your x-intercepts, but that goes from negative to positive. This stays positive to positive. Here we go from positive to negative. So that is going to be the x value for your maximum, which is at 3. So you're going to say g has a relative maximum at x equals 3 because, write this out, g prime, do not say the graph, name it, goes from positive to negative. And that would suffice. So for part C, find the absolute minimum. We love these questions. Absolute minimum of your interval on of your function on an interval. So how do you do that? We just wrote it out on the other one, didn't we? Or it was the mosquitoes one. Find your critical numbers, and then you test critical numbers and endpoints into the original. So if you don't have the original, which in this case they gave you the original, g of x is this. Okay, so first we got to determine our critical numbers. So where, because we're talking about g, so we want to know where is g prime of x, 0 or undefined, which is not undefined anywhere, so we just care about where it's 0. So these x-intercepts at -4, at 1, and at 3. And so we're going to create a table. Nope, not F. We're using G, right? Finding, whatever you're finding the absolute maximum of should be what goes there. And I'm going to write my critical, and then my endpoints are -5 and 4. And I'm plugging those into G. And what is my G function? It's this integral, right? It's the integral from -3 to x of f of t. So I'm going to be plugging these in for x, not for t, just for the boundary. So from -3 to 4. So how do we know from -3 to 4? We're going to find the area using our f graph. So that integrals, just like how we did it here. We're going to have to use the area. So from -3 to 4. -3 is here. 4 is over here. Well, we know from -3 to 0, we already did that, is 9/2, right? Okay, so here's tricky. Because this is a semicircle, but we're finding the area underneath it. Right? So how are you going to know this area, this weird area underneath it? You got to first think about it as a rectangle. So what is the area of just this rectangle I'm drawing? you guys should see this. Oh wait, I can't when it's on video. The base would be, it goes to 2. The height is 1. So the area of the rectangle is 2, base times height. And then we want to take away this white space, this semicircle area, and we'll be left with the area I'm shading. So you're going to have to do the 2 minus, now the area of the semicircle. So semicircle is 1/2 pi r squared. So what is our radius? It's half of the distance across the circle. So if the whole distance across your semicircle is 2, the radius would be 1 squared. So we took the area of the rectangle, subtracted this white area of the semicircle, and we're left with this shaded blue area under the curve. And that would be 2 minus, this is just pi over 2. And I would probably leave my answer like that for now. Oh, well, you know what? We're not even close to being done. So that was just that section. Now we're trying to go all the way to 4. So if we think here, though, these areas should cancel each other out. Aren't they the same? Looks like it to me. It's a triangle with a base of 1 and a height of 1, which we can write them if we need it later. The area would be 1/2 times 1 times 1. It's a triangle, 1/2 base times height. So 1/2. And this area down here is the same thing, but it's underneath. Since it's underneath the x-axis, we treat that area as negative. So that'd be, oops, negative 1/2. So when we're adding up all the way from -3 to 4, we know those cancel each other out. So you really just have 9/2 plus this. That was kind of, I hope that made sense. If you need to, pause the video and really think about all this area. Plus 2 minus pi over 2. This is the area of the trapezoid. This is that area under the semicircle, area of a triangle, area of the triangle underneath the x-axis. Okay, so and you could evaluate this even further if we need to. I'm just going to hold on to it. I might be able to figure it out without doing it. Here, we're going to do the integral from -3 to 1. So -3 to 1. -3 is here, 1 is here. Okay, so we know -3 to 0 is 9/2. And then we have 0 to 1. So that's half of this area. So I'm trying to think the best way to write this out. So half of, I'm trying to think, because it would be, two minus pi over 2 divided by 2, right? Or you could multiply it by 1/2. Maybe I should have done that. Sorry. Ignore this. I want half of this area from 0 to 1. So I'm just going to multiply my area by 1/2. So that would be 1/2 times 2 is 1, minus 1/2 times pi over 2 is pi over 4. 1 minus pi over 4. Okay, now 3. So the integral from -3 to 3 of f of t dt. So -3 to 0 is 9/2. Negative to 3. So we know this area under the semicircle is 2 minus pi over 2. And then we know that from 2 to 3 is a triangle with the area of 1/2. So it would be 9/2 plus 2 minus pi over 2 plus that area of the triangle, which was 1/2. So we can already see, like, this is going to be larger than this, right? And also this should be larger than this. So you don't have to actually evaluate them. Okay, now we're going to do our endpoints. Sorry, I'm looking because something's off. I always get worried that something's wrong. It's this one. Oh, let's just finish. So negative 5. So we're going to do the integral from negative 3 to 5 of f of t. So negative 3 to 0 is 9/2. What do we know about? Oh, it's negative 5. Okay, I was confused. I'm struggling over here. Negative 5. Which, if you notice now, our a is bigger than our b. So we need to flip it and negate it. So it's equal to the negative integral from negative 5 to negative 3 of f of t dt. So let's find the area from negative 5 to negative 3. Negative 5 is over here to negative 3 is right here. Well, what do you notice? Those negate each other. This is the negative area of this positive area. So we know that that's just 0. And then we have 4, so negative 3 to 4. Oh, that is why. I already did 4. That should have been negative 4. So what I'm going to do is change that to positive 4, make this one negative 4. So again, now we need to switch those boundaries. Change this to be negative 4 to negative 3. I'm rewriting this. Negate it because we're switching the boundaries from negative 4 to negative 3. So from negative 4 to negative 3, that is this triangle with a base of 1 and a height of 2. So it would be 1/2 times the base times the height, which would be 1. So the integral is 1, but we had to negate it, so it's negative 1. Okay, so we did all that. And now what are we looking for? Is we're looking for the absolute minimum value. So the smallest one, well, this is the only negative, right? These are not going to become negatives. If you think about those or add them up, the only negative, JMac, is going to be this one. So it didn't ask for where, it asked for what is. So that is this y value. So we'll say the absolute, if I could spell, minimum on, and we'll say our interval negative 5 to 4 is negative 1. Okay. Now we got D. So D says find all the values in the open interval where the graph of G would have a point of inflection. So what do we know about a point of inflection? You have a point of inflection when, you can think about it two different ways, when either G double prime switches from positive to negative. But if you think about it, we don't have G double prime. So use that to think about what does that mean in terms of G prime. Or when G prime, think about this is the slope of G prime. So what does it mean if your slope switches from positive to negative? It switched from increasing to decreasing. Or obviously the opposites. Or decreasing to increasing. And this could have been or neg to positive. So for what values does G have a point of inflection? Well, since we have the G prime graph, we're going to see when does it switch from increasing to decreasing or decreasing to increasing. So it switches here because it was increasing and now it's decreasing. So at x equals, what is that? Now I've written all over this. Oh, well, there's the point right there, huh? Negative 3. And then it's decreasing. Now this is still decreasing and until you get to the bottom of the circle. And then now it's increasing. So that's x equals 2. And then where else? Right here. No, that's not x equals 2. That was x equals 1. But then also at x equals 2, it switches back to decreasing. So you should have 3 different POIs. And we'll say at these 3 spots, g of x will have a point of inflection, and then because, and now you could technically use either of these reasonings. I think because we were looking at g prime, it makes more sense to use this one. But if you use this thought process and just used it with this graph and thought about the slope, you could also write that down. G prime of x switches from increasing to decreasing, or decreasing to increasing. So this is really what I would write down on your test. I just write this down to think about it ahead of time. You don't have to write that down. You'd want to kind of summarize it in a nice sentence. Okay, so that is our last, well, I did them out of order. Not probably your last free response, but my last free response. So these were a lot, so hopefully you're just doing these as you need them, and hopefully you try them on your own before you watch these videos. I don't know why I'm saying it at the end of the video, but let me know if y'all need anything as you're working on these.